final talk of this session, and it will be given by Sir Anthony K. Cheetham. And Mr. Cheetham is currently research professor at the University of California, Santa Barbara, and also he is a distinguished professor at National University of Singapore. And today he is going to talk us about the hybrid perovskite formats. Formats of metal is aluminum, manganese, iron, etc. for carbon captures and hydrogen storage. Professor Cheetham.
Thank you very much, Tapas. Is my mic working as well? Yeah, good. Thank you very much, Tapas, and for the kind introduction. Mohammed and I always end this meeting, and so he always gives this dazzling talk with beautiful graphics and so on, and on these fabulous MOFs, lots and lots of different structures. I'm a poor old man, and I can't afford the kind of ligands that Mohammed's working with. And so I've been looking around to see if we can find something simple that we can afford in our laboratory and see if it will actually do anything. So I'm going to talk about formates, and formate perovskites in particular. And sort of brief overview of the talk, I'll just remind you what a perovskite is, very briefly, both inorganic and hybrid perovskites. Specifically, I'll mention a few hybrid perovskite halides, which we heard a lot about at the beginning of the meeting in the context of things like the methyl ammonium lead iodide. We've done a lot of work on those and the formates. And then I'm going to talk about some formates that are perovskites, but they don't have cations in the cavity. So you'll see what that means. And we're going to talk about using these for some of these separation processes that Mohammed mentioned at the beginning of his talk. And we'll see where that takes us. So probably nearly everybody in the room has seen the perovskite structure. The classical inorganic perovskite is calcium titanate, and the crystal structure was determined almost 100 years ago. And examples are barium titanate, which is very important ferroelectric, the high temperature cuprate superconductors like the Iberco. There are ferromagnetic perovskites, magnetoresistive systems, multiferroics, and so on. And the perovskite world has evolved over the last 100 years, from the first perovskite to the inorganic one, which was characterized in 1925. In 1978, there was an important paper where a group in Stuttgart with Weber and co-workers made the first hybrid perovskites where they put an organic amine cation into the cavity of a lead halide perovskite. And so one of the materials they made was actually the methyl ammonium lead iodide that everybody talks about. And it was another 30 years before people realized that that was actually a really interesting compound that spawned a massive amount of work. And at the time, they were making it just for curiosity and so on. So there's a good lesson there. And then the next evolution was with Song Gao's group in Beijing. He's no longer in Beijing, he's at Sun Yat-sen University now, the president, where they replaced the linker. So instead of having, say, oxide linkers or halide linkers, they made polyatomic linkers, and in particular the formate. So they made things like dimethyl ammonium, manganese formates, ABX3 formates of that type. And we've done a lot of work on those. They're very interesting. We discovered that they're ferroelectric and multiferroic, and I've talked about this in this forum previously, so I'm not going to discuss that today. But what we've been doing in the last 5 years or so has been to continue work on the halide perovskites, focusing on things like double perovskites. Pratap Vishnoi mentioned some of the work that he did when he was in Santa Barbara on ruthenium, Highlights just recently, we've kind of trebled the number of known single perovskite iodides, hybrid iodides. So we've made things like methylammonium rare earth iodides and methylammonium strontium iodide and so on. So this family is actually bigger than people had thought. I was absolutely amazed that nobody had tried to do this, or if they did try to do it, they didn't succeed. But we've made this and just published it in JACS just at Christmas time. On the formate side, apart from the formate perovskites of the type that show ferroelectric properties, we've been focusing on aluminum formate, and that's going to be primarily the focus of this talk. So aluminum formate has the rhenium trioxide structure. So on the left, you can see the classical perovskite with the A cation in the cavity, whether it be strontium or methylammonium or whatever. If the charge of the species is such that you don't need a cation in the cavity, then you have the rhenium trioxide structure, which is shown in the center there. And it's an extended three-dimensional array. It's an incredibly simple structure. And curiously, it's basically the structure of MOF5, which is one of Muhammad's great discoveries. And so it turns out that you can make these ReO3s, and we wrote a review about this 3 years ago or so in Nature Reviews Materials, and showed, much to our own surprise, and I think everybody else's, how many rhenium trioxide families there are, not just oxides and halides, nitrides, arsenides, hydroxides you can see, and in particular formates that we're very interested in. So I'm going to talk about aluminum formates, and I would claim it's the world's simplest metal organic framework. It's definitely a poor man's MOF, and of course, aluminum formate is not new. You might imagine that other people reacted aluminum salts with formic acid in the past. And so it's in the Gmelin handbook in 1933 without any characterization. And then there's a Russian report in the 80s that showed a powder pattern of the aluminum formate, but didn't characterize it in any way. And then the first sort of major step in understanding them was a paper in 1999 by Daniel Gatteschi in Italy, showing that you could make manganese formates with the rhenium trioxide structure. And that was followed in 2007 by a really nice paper from China by Qian and co-workers in organic chemistry, where they made the aluminum formate, the gallium formate, indium formate, iron formate. So you can make these with, quite a family of trivalent metal cations. But at that point, in a sense, they were not MOFs. And what all of these materials, the Gatteschi ones and the Qian ones, had in common is that when you crystallized them out and did the crystal structure, they actually have carbon dioxide in the cavity, as you can see there. And I noticed this, and when we were doing the review, I looked at this paper by Qian, and I thought, well, that's an interesting thing. And the title of the paper was Templating of Aluminum Formates by Carbon Dioxide. And so I asked myself two questions. One was, first of all, if there's CO2 in the cavity, can we get it out without collapsing the structure, which nobody had done before? And if you did get the CO2 out without collapsing the structure, would it then act as a highly selective sorbent for carbon dioxide? So we set about doing that with my one-man team at the time in Singapore, and we did all the usual things that you'd expect, like thermogravimetric analysis to show that it does lose all the stuff from the cavities. There's some other stuff in the cavities, but I'll go into the details in a minute. But when the stuff comes out of the cavities on heating, it actually doesn't collapse. And you can see from the X-ray pattern on the right-hand side that it's actually stable to about 250 degrees C before you start to see any collapse of the structure. And this was finally published in Science Advances at the end of 2022 after a titanic struggle with the referees that took 18 months. It was the referees of science, and the scientific referees were great. The engineers gave us a torrid time, but it finally appeared. And in a way, as you'll see, we got the kind of last laugh on this. So we took that completely solvent and CO2-free structure of aluminum formate, which we call ALF. So this now is a genuine MOF. It's a porous MOF. And we did the crystal structure of it by the Rietveld method. We've been doing Rietveld methods since about 1972, so we're sort of reasonably expert at this. And we did this with my former co-worker, Hayden Evans at NIST, and where they have a fabulous setup there, though their reactor's been shut down for the last couple of years. And so we're able to do the structure. We did it as a function of temperature. And so this has nothing in the cavities. It's a bit more complicated than I described so far because there are two different types of cavities. There's a slightly smaller and slightly larger cavity, and I'll mention that later. And then we found it will reabsorb carbon dioxide, and it will do it at room temperature, it will do it at higher temperatures, and the heat of adsorption is quite substantial, about 47 kilojoules per mole. So this is a high surface area MOF material that will absorb CO2. The green line is the CO2 isotherm at room temperature. The blue line on the bottom is what happens if you don't activate the material. If you take the material that's been described before that has stuff in the channels, of course it doesn't absorb anything. So it will reabsorb it, and so this looks quite exciting for sort of various applications. We did further detailed neutron studies on the location of the CO2 in the two different cavities, the smaller cavity on the left there at the bottom, where the CO2 is absolutely perfectly sited for hydrogen bonding between the oxygen and the CO2 and the hydrogen atoms of the formate linker. And so that's really tightly bound. And then the other cavity slightly larger, and when we reabsorb CO2, the CO2 goes in there, and we followed it in real time as we were dosing. They have beautiful equipment, so we can dose it in real time and follow the uptake and the population and the two different cavities and so on. So if we could fill all of both cavities, the composition would be down at the bottom there, aluminum formate 3 times with 1.0 CO2. As it is, we don't quite fill all of the cavities up at 1 atmosphere, so it comes to be about 78% filled of CO2. So since we can capture CO2, could it potentially be used to capture CO2 from flue gases in power stations? And so the first separation that we looked at with this was to see, will it adsorb nitrogen? Because most of the flue gas is nitrogen, and people, of course, want to capture the CO2 from things like coal-fired power plants. So we looked at nitrogen adsorption, and much to our surprise, it does not adsorb any hydrogen at all. Even though, as Mohammed's just shown you, the difference in size between CO2 and nitrogen is like 0.2 of an angstrom, the kinetic diameter. It's extremely small. But nitrogen won't go into the cavity. And so when we take the two isotherms and look at the selectivity of CO2 versus nitrogen, it's in the range between 350 and 500. It's a phenomenally selective material. So yes, it does have the potential to do this CO2 capture from flue gases. And so by now, it's starting to get quite excited, because if you're going to address a problem like CO2 in flue gases from a power plant, then power plants burn tens of thousands of tons of coal every day. So the amount of CO2 they're producing is tens of thousands of tons of CO2. And so you have to have something that is literally dirt cheap. And I'll show you that this is dirt cheap, and it's probably the only material that you could scale up to the level that you would need to make a real impact on a major societal problem such as CO2 in power stations. So we've done DFT calculations with my colleague Piero Canepa and Jerry Deng in Singapore. And interesting thing is, the small cavity absorbs the CO2 more effectively than the larger cavity, so we get different heats of absorptions from the calculations. They agree overall rather nicely with our experiments. When you look at the nitrogen absorption, there's no reason why nitrogen wouldn't be absorbed. It's not as good as CO2. It's 28 kilojoules per mole or so. It's about the same in both cavities, but it doesn't go in. So that tells you that there's a kinetic reason, and there's essentially a size effect that prevents the CO2, the nitrogen, from going in. Water's smaller than both CO2 and nitrogen, and so the thermodynamics for putting water into it are very good, but it's kinetically very slow, which turns out to be important. So at least kinetically slow at room temperature. So we got a really good understanding of the energetics of CO2 and nitrogen in the cavities, of the heat maps for the different cavities and so on. So to a first approximation, this is a size selective process where the smaller CO2 molecule, even though it's so much, sort of minutely smaller than nitrogen, will go into the cavity and the nitrogen won't. But it then gave me, when I looked at this table of sizes, I thought, well, if nitrogen won't go in, maybe oxygen, which is slightly smaller than nitrogen, will go in. And so can you do non-cryogenic separation of air into oxygen and nitrogen using ALF? And so we tried that. Typical composition of oxygen in air, as you'll all know, sort of roughly 80% nitrogen, 20% oxygen, with a bit of argon and a minute amount of CO2. Though Mohammed showed us how his brilliant MOFs can actually absorb CO2 directly from the air, even though it's 0.04%, but it gives you an idea of how difficult that is. And air separation is normally done commercially in two different ways. One is by cryogenic distillation at low temperatures, so you liquefy the air, and then you do a distillation, separate the oxygen and nitrogen based upon their different boiling points. The other way you can do it, which is also commercial, is to use lithium-containing zeolites. And lithium-containing zeolites are used. You might see people with these portable oxygen apparatuses that they carry around. Those normally use a lithium zeolite. And lithium zeolite works quite well. The separation factor for oxygen and nitrogen is about sort of 5 or 6. So it's small, but it's not bad. The problem with the zeolites is that they absorb the stuff that you don't want. So they absorb the nitrogen, which is 80% of the air. So in order to get to the oxygen, you have to, first of all, remove 80% of the air in terms of nitrogen. And so this is obviously not ideal from a sort of engineering point of view, but that's the way it is. And hitherto, there have been no really good materials that absorb oxygen very selectively, as I'll show you that ALF does. So here's the separation. Well, this is on the left, the adsorption isotherm of oxygen into ALF. And down at on the right-hand side, there's the nitrogen. So you see it doesn't adsorb, as I said. The oxygen goes in very well. It goes in optimally at about 200 Kelvin. It goes in at room temperature, but not as much as we would like, at 1 atmosphere. But then as you cool it down, it's optimal at about 200 K, and then it goes down again. So the selectivity's around about 100, so it's more than an order of magnitude better than the zeolites, and it absorbs the oxygen instead of the nitrogen. So this is not the most versatile of MOF. One of the things that Mohammed's shown, how you can fine-tune things with all his sort of design strategies and so on. There's not a heck of a lot that you can do with ALF, but one of the things you can do with it is substitute other metals, such as iron. And so it turns out that when you dope iron into the ALF, iron's a bit bigger than aluminum, and it expands the window and the cavity a little bit. So it improves both the kinetics and the capacity for absorbing oxygen. So that story is a little bit more complex than I've told it, but that's sort of, to a good approximation, how this works. So the energetics of absorption of oxygen shown here just show that oxygen absorption is more or less the same as nitrogen, around about 24, 25 kilojoules per mole. So it's not as good as CO2, and that's why you have to cool it down to get the optimum capacity. That turns out not to be a big problem. First of all, 200 Kelvin is dry ice temperatures, so you could just use dry ice. It's not regarded as cryogenic, so you could actually just use dry ice if you wanted to do. But we're looking now at medical oxygen. You'll all remember during the pandemic how there were shortages of medical oxygen all over the world, and especially in developing countries, because lots of places in rural areas, they don't have access to cryogenic distillation. The availability of the lithium-based systems is not great. And of course, lithium's very expensive too. So we're looking with colleagues at the Jawaharlal Nehru Center in Bangalore, where the Sheikh Sakar lab is, we're looking at the possibility of producing low-cost medical oxygen. And medical oxygen typically would be about 95% oxygen. And our separation is so good, I mean, the purity is not going to be a challenge at all. So Professor Diwakar in Bangalore in chemical engineering has a startup company that already uses zeolites to do this. And so he's now adapting his pilot plant to do it with ALF. And Pratap Vishnoy, who's been here at the meeting, is helping locally to prepare the sort of bulk quantities of ALF. And so the Diwakar's idea, which I thought was great, and I've not been so ambitious, he said, we don't really want to cool it, but what we can do is just use higher pressures. And because even at room temperature, if we use higher pressures, we're going to get quite good capacities. So our aim is to use a pressure swing adsorption cycle at pressures between kind of 0 and 6 atmospheres. It's not very high. And I'm hoping, by the end of this first quarter, we'll know if we can do that. The kind of immediate challenge is to make about 10 kilos of ALF, which Pratap is helping with, and also to pelletize it. We, in the lab, like probably nearly everybody here, we make pellets one at a time in a pellet press. So if you've got 10 kilos of material and want to make pellets, that's not a very good way of doing it. So we need to find someone who's well set up to make pellets over there. And we'll need a drying step because the ALF is sensitive to water, but these zeolites are much more sensitive than ALF, and so all these systems already have a drying step as part of the process, so they dry the air before they do the separation. So that's quite exciting. And led us to other things. Since we know we can separate CO2 from nitrogen, maybe we could separate CO2 from hydrocarbons. And the obvious one to do is separating CO2 from methane, which Mohammed's talked about. because biogas, for example, has a large amount of CO2 in it, depending where and how you make it and so on, but between about 25 and 50%. There are also natural gas wells all over the world that have huge quantities of CO2 in them, again, as high as, say, 30% or so. So we've looked at the question of separating CO2 from hydrocarbons, and there's a lot of data on here. Let me just give you the headlines. I can't even see it myself from here, but one of those adsorption isotherms is the CO2, the one in the top left-hand corner, compared with a whole range of, let me just try this, compared with methane, propane, ethane, ethylene, and even acetylene. So this is the adsorption of all the small hydrocarbons compared with CO2. And so the selectivity for CO2 over hydrocarbons is phenomenally good. So in the case of CO2 versus methane, it's round about down here, it's between 10 to the 3 and 10 to the 3 and 10 to the 4. And for CO2 versus acetylene, it's between 10 to the 5 and 10 to the 6. And so compared with the other materials that are used to do these separations, which are shown in these charts here on the left, I mean, ALF is a complete standout, just in a different league from all the other things. So this is just a kind of, if I was religious, I would say it was an act of God that this simple moth will do so many wonderful things. And it's basically because that window into the cavity is sort of exquisitely precise that enables it to absorb selectively small molecules from just slightly larger ones and so on. So this has been exciting. The driver of this part of the work was my colleague Dan Zhao in Singapore and his group who are really well equipped for doing the kind of thermodynamics and adsorptions and breakthrough experiments and all the things that people expect to see. So Dan's group have done that. So let me just come to the pros and cons of ALF. And the main pro of ALF is that it's just so simple to make, and you only need two things to make it. I could teach my little granddaughter how to make it. You need aluminum hydroxide and formic acid. You don't even need a solvent because the formic acid acts as the solvent as well as the reagent. The materials cost of ALF is about $2 a kilo, and so it's, roughly, conservatively, it's sort of at least 10 times cheaper than any other moth, I think, and 1,000 times cheaper than many of the moths out there. So it's just incredibly cheap, and because it's made from commodity chemicals, which are very widely available, you can make it at scale. And so even in the lab in Bangalore, we have in Singapore, we've made kilogram quantities and just taking a large round bottom flask and sort of stirring it as best we could and so on. So we don't have equipment for really scaling it up there, but it's easy to make, and you can make kilo quantities. The other thing about it, it's got fantastic mechanical properties. We've not measured the moduli because we've not got around to doing it, but you can calculate them very well when you know the crystal structure. So when we calculate the Young's modulus, bulk modulus, shear modulus, and so on, they're similar to a zeolite rather than a moth. And moths are notoriously fragile, especially the ones with kind of large cavities. Whereas with this, we can make pellets of 15 tons without any problem, and we can ball mill it without losing crystallinity. We can actually make nanoparticles of it just by ball milling of it. So it has a lot of advantages. The Achilles heel of ALF is that it's sensitive to water above about 30 degrees centigrade. So it needs a drying step for any process where there's heat and water involved. Either that, or you need to do something to it to make it hydrophobic. And so the tranche of work that we're doing at the moment in Singapore, which is more or less finished, and I'm going there tomorrow night, so I'll be able to sort of bring it to a conclusion, has involved making ALF hydrophobic by making kind of composites with hydrophobic polymers. And we can do that without significantly altering the cost advantage. So the other obvious molecule to absorb would be hydrogen, because that's smaller than CO2 and oxygen. And so could we use it for hydrogen storage? And as Mohammed mentioned, there's a huge amount of interest in hydrogen storage, and it's a problem for any future hydrogen economy. So people use MOFs, but they focus on MOFs with under-coordinated metal sites, which Jeff Long, for example, has done a lot of work on, where the hydrogen will bind to, say, nickel or metal of that type. People use carbons, but carbon, especially if there's a separation involved, carbons are not great, but they're cheap. And then, of course, the comparison always has to be with compressed hydrogen. And when people store hydrogen under compression, they use about 350 atmospheres normally. So that's, serious pressure. So ALF does go into, hydrogen does go into ALF extremely well. Of course, interactions between hydrogen and a framework, whether it's ALF or any other one, are much weaker typically. And so you have to cool it down more. So the optimal adsorption is it's about 120 K. You see on the left there the adsorption isotherm. It's sort of reasonably decent up to even up to room temperature at higher pressures, but at 120 K it's really good. And it's got a capacity of about 11 grams of hydrogen per kilo of sorbent. Now the Department of Energy has a target which is 18 grams of hydrogen per kilo of adsorbent, and we're only at 11, but their cost target for the MOF is $10. That's the aspiration, where our cost is down at $2. So our cost of storing hydrogen is about, we get 5.5 grams of hydrogen per dollar, whereas the DOE target is 1.8. So we're kind of 3 times better than the target. So the beauty of ALF, you don't have to have the best performance for these large-scale things because it's so cheap. But so if we're reasonably good, nearly as good as the others, then the chances of anybody making a cheaper MOF than ALF is going to be vanishingly small. So this was published in JACS just before Christmas, and we've done neutron diffraction work on the location of hydrogen. So it's very localized in the small cavity, a bit like the CO2 was earlier, but in the large cavity it's sort of delocalized quite a lot away from the center, but we can fit that, we can model that quite well, and we've followed the uptake of hydrogen as a function of pressure and compared that with our adsorption isotherms. So, and again, the neutron things that Hayden Evans did are absolutely stunning. And with this work, we've been working a lot with colleagues at NIST, not only Hayden Evans at NIST, but also Craig Brown and his colleague Tanner Yildirim, who are sort of hydrogen specialists. But we've also worked with Hannah Breunig at Lawrence Berkeley National Lab, and because they're specialists on doing techno-economic analyses. And so in our paper in JACS, we published a techno-economic analysis. And what it shows, at the top left-hand side, you can see the capacity of hydrogen in ALF at 120 K compared with compressed hydrogen. So, of course, the compressed hydrogen is much better. But we're at 15 atmospheres, and they're at 350 atmospheres. So there's a stunning difference in pressure. And for a lot of applications, you don't want 350 atmospheres because you've got to step down the pressure, say if you're using it with a fuel cell. Now, I'm not going to buy a car running on hydrogen with ALF because my range will never be as good as Jeff Long's compounds and so on, though he may not be able to afford to fill the tank because the MOF is so expensive. But where this comes into its own is for large-scale hydrogen storage. So there's a lot of interest in the Department of Energy for storing hydrogen to use with fuel cells at things like data centers, as in, backup systems at data centers. And this is absolutely perfect for it. And it basically has a sweet spot. If you look at the figure on the bottom left there, this is where ALF is best for hydrogen, sort of intermediate temperatures and low pressures. The kind of conventional MOFs are over here, and then some of the more specialized ones are up here. But when you have large cavities, you need more pressure. And so this is a case where having small cavities gives you an advantage and better absorption at low pressure. I mentioned that we got our revenge on science because when we originally published the Science Advances paper, one of the science journalists got in touch with me and said he was really interested in it and so on, and could he write about it? But then it didn't happen in time for their publication, and so it never happened. Anyway, I saw the opportunity to keep him informed of the progress of our work with air separation and CO2, and then finally hydrogen. And so he did actually write about it in the fall, just after round about the time that the hydrogen paper was published in JACS. And so there's a JACS feature article by Robert Service on the potential of ALF for fuel cells and so on. So here's an overview of the technology possibilities: medical oxygen, biofuel, CO2 capture, fuel cells, and so on. And we, of course, not only have publications, but also some patents. There's another thing which is fascinating for me, which I've thought about a lot, which is, can we use ALF for CO2 mineralization? Now, it turns out that progress on CO2 reduction, which we've heard quite a lot about, is particularly good for making formic acid. And there's a company in Richmond, Washington, called Ocochem, which has a process for making formic acid using the cheap electricity that you can get in Washington from hydroelectric power. And so they reckon they can make formic acid for 65 cents a kilo. And for our costing, we've been estimating about $1 a kilo. So, and there's a lot of formic acid goes into this. It's, in terms of weight, it's the largest component in the reaction. So they can make very cheap formic acid. Aluminum hydroxide is very cheap. And so you can react their formic acid with aluminum hydroxide and you make ALF. So essentially you've gone from CO2, water, electrons, and aluminum hydroxide to make ALF. And if you calculate what's the weight of CO2 in the framework of ALF, it's 81%. So this is not adsorbed CO2, this is CO2 that's wrapped up in the framework as the formic acid group. And so if you add in the CO2 you could put in the cavities, it goes up to 85 weight%. And for comparison, calcium carbonate's 44 weight% CO2. So there's a big advantage in having aluminum because it's so light. And then if you look at MOFs storing in the cavities, then the absolute maximum absorption is about 27 weight%. So this is a really interesting option for CO2 mineralization. So conclusions and future developments. These formates with the ReO3 structure are emerging class of sorbates. They're scalable, earth abundant, low cost, really easy to make, and they've got some really exciting properties. Aluminum formate's particularly attractive. It's the most stable one. And the reason the previous people never succeeded in activating it is that they tried to do it with the iron compound, the pure iron compound, and it's not as stable, and so they failed and they gave up on it. But aluminum is more stable, and there are lots of interesting possible applications, which I've talked about. And then what we're doing at the moment, amongst other things, we have made analogues of ALF that have not been made before, like vanadium formate and chromium formate and so on, and a lot of mixed aluminum, iron, aluminum, chromium, etc. And we've been working on this the sort of water sensitivity, making it hydrophobic, and that's sort of more or less come to a conclusion. And we're working on noble gas separations as well, because we'll be able to separate argon from air quite straightforwardly, because and we know that we can do that already. So I acknowledge my collaborators, mentioned most of them. The guy who first made this in Santa Barbara and activated it was an Indian young man called Dinesh Mulangi, who's now in the States, a super guy. And then his successor, who's been doing the work on the hydrophobicity, is Rajesh Das, who joined me sort of last year. And then the senior collaborators, I think I mentioned most of them already. And this was done with about $140,000 from Singapore. So I adore the simplicity of it and functionality. And on that note, a beautiful view of UC Santa Barbara, and I thank you for your attention.
So we can have a few questions. Can I ask?
Shirley has one. You can, of course.
Thank you, Tony. I think I learned quite a bit about you can actually use the oxygen for medical purpose using your aluminum formate. In terms of the collection, once it's stored, how would you collect these oxygen into the medical usage? I was just curious if...
They just put it in cylinders like you'd have in the lab. So that people who use medical oxygen normally use it from cylinders. And of course, if it's portable, then they have it hanging from their hip. And if it's in the hospital, typically they just have a rack of large cylinders.
I see. So the efficiency for transferring is not a problem at all. Unlike, sometimes when you do the loss can be quite significant and...
Our system will be portable.
I see.
So it would go on the back of a pickup truck. And so you don't have to, and then you can separate it where you want to, where it's needed.
Yeah, okay. I think that's a brilliant basically local production and the usage of the gaseous species.
Yeah, exactly.
Yeah, thank you.
No energy needed.
No energy.
And no energy needed, yeah.
Tony, lovely talk. I can see the huge benefits of using ALF for gas separation, but in terms of CO2 capture, you're going to have to use a lot of bauxite. You have to dig out a lot of bauxite from the ground to capture enough CO2, right?
Yep.
So maybe it's not so good for that.
Well, if you're going to have any metal involved, using something that's come from bauxite is about as good as it gets. I mean, aluminum oxide or hydroxides are about the cheapest oxides you can buy because the abundance of aluminum is so high and it's available kind of ubiquitously. So,
but I mean, you're competing with just pumping it straight into the ground.
Oh, I see what you mean.
Yeah,
but people are nervous about pumping it into the ground because they think it might come out again if there's a seismic event or something like that. If you tie it up as ALF, then basically you're taking the bauxite and the CO2 and putting it in the ground as a stable inorganic material.
And it will be very stable over time. Yeah, okay. Thank you.
Any other questions? Okay, so I have one question, Tony, here. So you told that it is not stable, yeah, means to water.
Yeah.
So if you want to, in application in the oxygen concentrator, so not only you have to lower the temperature to the dry ice, but you have to again separate the from water, means the humidity you have to.
But that's standard in air separation.
Okay.
So if you're doing it cryogenically, they have to have a drying step. And the drying steps are super cheap because you do them with, a zeolite X or something like that. And with the portable ones using lithium zeolites, they have to have a drying step as well. So all the commercial thing with your colleague in Bangalore, it already has a drying step. Okay. Because if you use a zeolite and you don't dry the air, then the water will block all the sites where the nitrogen would be absorbed. Okay. So it's not a big deal.
Okay, so let's thank Professor Cheetham for these wonderful presentations.